Have you ever wondered how your computer juggles dozens of applications at once, seamlessly switching between a video call, your email, and a complex spreadsheet, all without missing a beat? It creates the illusion that everything is running simultaneously, but beneath the surface, there is a fascinating ballet of resource management constantly at play. The overhead of a single context switch refers to the time and resources the operating system spends to stop one process or thread and start another. It is not a fixed number, but rather a variable cost that typically ranges from a few microseconds to tens of microseconds, depending on the system architecture, hardware, and the specific operating system. This overhead includes saving the state of the current task and then loading the state of the next task onto the central processing unit. This overhead arises from several crucial operations. First, the central processing unit's register set, which holds temporary data for computations, must be saved to memory for the exiting task and then restored for the incoming task. Second, the translation look-aside buffer, or TLB, a small cache that helps translate virtual memory addresses to physical memory addresses, often needs to be flushed or partially updated. This is because different tasks have different memory maps. Finally, and often most significantly, context switches can lead to cache pollution. The data that was hot in the central processing unit's L1, L2, and L3 caches for the previous task is likely irrelevant for the new task, meaning these caches must be refilled with new data, which is a comparatively slow operation. To minimize the impact of context switching, developers often focus on reducing the frequency of switches and optimizing the processes themselves. Techniques include using larger time slices for tasks where appropriate, designing applications with efficient input and output operations that do not frequently block, and employing asynchronous programming models. By grouping related work and minimizing unnecessary interruptions, systems can reduce the need for the operating system to perform these costly state transitions. Understanding the mechanics of cache invalidation and TLB flushes gives you a deeper insight into system performance. While a single context switch overhead might seem minuscule, in highly concurrent server environments, where thousands of switches occur every second, the cumulative effect can significantly impact overall throughput and latency. This becomes especially relevant in high-performance computing or real-time systems where every microsecond counts. Ultimately, recognizing the overhead associated with context switching empowers you to design and build more efficient and responsive server applications. It helps you appreciate that the perceived seamlessness of multitasking comes with an underlying cost, one that careful system and application design can effectively mitigate, leading to better resource utilization and a smoother user experience.
If this helps you code smarter, like, subscribe, and stay tuned for more.